Welcome, safety enthusiasts, to the latest SRES Fireside Chat. I'm Jody Nelson, and I'm joined by my colleague Gokul, who you probably know from previous Fireside Chats. So, as always, if you have any questions during today's discussion, please put your questions into the chat, and we'll try to answer them as best we can. So, today we have two special guests from Visage Technologies, Draco and Ivan, both experts in building AI products in a number of different industries. Today, we're going to discuss and have our discussion centered around challenges associated with verification validation, specifically for AI-driven systems, as introduces new, challenges that we didn't have typically in our V&V activities. But before we get started and diving into that conversation, we'd like to first welcome Draco and Ivan. Thank you for joining us here.
Hello.
Maybe you can do an introduction of Visage Technologies and yourself. Maybe Draco, if you could start.
Yeah, sure. Hello, everyone. I can take that question first and say something about Visage Technologies. So, Visage Technologies has been working in computer vision and AI for over 2 decades. We were founded in 2002 in Linköping in Sweden by computer vision scientists. Our founders actually were among the main contributors to the MPEG-4 face and body animation standard. And today we have around 180 engineers across our offices in Sweden and Croatia, with technology used by more than 300 clients worldwide. And since 2015, one of our core business has been dedicated to ADAS development in close collaboration with the automotive industry. Real-time computer vision on embedded automotive hardware and also developed to the standards and rigor to the industry demands, actually. And that ADAS experience is the foundation we are now building on as we broaden into new domains. We are extending our perception and safety expertise to off-highway machines like construction, agricultural, and mining equipment as well, to industrial vehicles, to mention a few, mobile robotics as well. That ranges from safety functions like human detection and collision avoidance, all the way to perception for fully autonomy and in unmanned ground vehicles as well. Myself, I'm principal engineer in Visage, and I'm working on the development of ADAS functions for almost 10 years now.
Perfect. Thank you. Ivan?
Yeah, and as for me, so I'm a senior R&D engineer here at Visage with the company for around 7 years by now. So most of my work has emphasis on the functional safety, and before this, I was also a development engineer in one of Germany's big tier one suppliers for 6 years. So also quite a long career with ADAS systems.
Great. Perfect. Well, thank you both for joining. And one of the reasons we wanted Visage to be here, they're practitioners of the standard, or practitioners of AI systems, right? That actually developing AI systems in different areas. And, as you know, probably from the SRES, we're focused around physical AI and, safety around that. So it's a good collaboration to have kind of their feedback. Those of you that attended one of our previous fireside chats, we spoke with Edward from TIFF SGS, and there we got kind of a perspective on AI safety from an assessor's view or an auditor's view. But with Draco and Ivan here, they're actually developing ML models and, working with the real products. So I think it's a good, interesting conversation we'll have here. And, one of the very difficult topics that we hear a lot from our customers is about validation. What is validation and how do we validate for these AI-based systems? So with that, Gokul, can you help me maybe kind of set the stage a little bit? Can you walk us through what V&V or verification validation looks like in kind of the non-AI world, where we're more rule-based but still safety critical? A lot of our systems out there today still are non-AI based, so it's very important to kind of understand, where we're coming from. And then maybe you can explain why there are new challenges that we face with systems that have, that learn from data, rather than explicitly being programmed.
Yeah, thank you. And it's a very interesting topic. Maybe to answer the first part of your question, I will point us directly to 26262, right? I think that's a good place to start. Um, so when we talk about verification validation in 26262, verification is something very specific, right? We're checking for correctness, completeness, and consistency, right? So every work product is verified. So typically you would use review as a verification method. You're going to have subject matter experts take a look and confirm. Second set of eyes check, checklist-based check to confirm that the activity was complete, the objective was met. Of course, we can also use more semi-formal methods, as we call them, right? Safety analysis, top-down, bottom-up type of safety analysis, which we can use to identify, okay, where are the gaps in requirements, right? Or maybe do we have a single point failure somewhere that we didn't really account for? So that will be considered as verification. And then, of course, we are not done there because so far we've only used either a mental model or fault models, but you also need to really test, right? So on the right-hand side, you perform testing to confirm that, okay, did I really implement the requirements I said I'm going to implement? And of course, is the timing okay, right? We don't have unlimited time. Also, are my safety mechanisms working under stress, right? So those are the types of things that we still confirm. Of course, we also want to mimic the real world, right, as much as we can to try to get to that confirmation or confidence. Of course, validation is something very specific. I know the industry generally uses VMVs more loosely, but 26262 very clearly says validation is only at the item level, right? At the vehicle level. So we can maybe even translate that to physical AI as the completed sort of product, right? That's where we validate. In validation, we are asking the question, did we build the right thing, right? Are our requirements correct? Are they valid? Do we have the right systematic approach to building this, right? Do we have any random hardware failures that we have to consider? Or have they been covered, right? So basically, we are looking for sufficiency, but also confirming that we built the right system that is safe. And all of this, again, is for rules-based approach. However, AI systems are probabilistic, right? So their completeness is very different. So even when we talk about verification in an AI-based system, we start borrowing principles. If you're in automotive, then you're very familiar with the SOTIF standard, right? Which sort of starts to build a framework for what a verification validation will be for ADAS and ADS systems. In that concept, what we are really looking for in verification is for the known scenarios, the scenarios that I've already encountered, or the scenarios that I could think of or perform an analysis. How good am I in um, uh, addressing them, not performing some undesired behavior, right? And in some of these cases, we will know that there is a known weakness, right? There may be certain scenarios where maybe we didn't have the data for our ML model, or maybe we had some requirement that we didn't specify, right? So in those cases, a known scenario could expose a weakness that we can eventually get fixed. And then how do we make sure that we actually fixed it? We do a lot of testing, right? And we confirm. And this can be a combination of track testing, can be on road, can be simulation-based testing. And those are something that we can think about. But a key aspect for probabilistic safety is also thinking about unknowns. Of course, thinking about unknowns is kind of a weird sort of thinking. How do you think about something that you don't know? So then it becomes an exploration exercise, right? So how much confidence do we have that we've explored our operational design domain enough, right? The scenarios in our operational design domain. How representative are our tests, right? To confirm that not only were we doing all the nominal sort of kind of quote unquote boring ones, but also interesting edge cases, corner cases. And then the argument for validation of an AI-based system is an argument of, have I sufficiently explored the scenario space, and can I build an argument that have performed certain number of scenarios that are representative of how many hours of operation of a physical AI system, or maybe how many miles of driving of a automated driving system, for instance. And it's a long-winded sort of response, but hopefully that sets the stage for really talking about the AI-based system.
And I think one of the difficulties is the term validation, right? Because those of us that kind of come out of the pure ISO 26262 world, validation is kind of like at the end, right? The standard even prescribes it at the end. And as you mentioned, it's a vehicle level kind of activity. And one of the things we see, and we talked about a little bit in our Fireside chat in the ISO 8800, there's validation data sets, right? When we get into the AI development side of things. And that's not really at the end kind of activity. We go through this process of training our model, but then we use the validation data set to, tweak the hyperparameters, set different parameters there. And, we're going to then use that trained model and then put unknown test data to it to confirm and have some metrics against that to see if it works as what we intended. Where, that term validation there it's more upfront, on the AI side. So
Yeah, and one other thing that I wanted to mention was it's not always safe, right? What if there's a corner case that you're trying to explore and then it's too dangerous? So that's where simulation comes in, right? Of course, we do simulation even for like more rules-based systems, but here I think we have to rely more on simulation, because even if we try to encounter, or even if we try to simulate a corner case, that could be too dangerous for whoever is testing on the car or the robot.
well, that's a good transition to my next question I had for Visage. We're talking about this validation for AI systems. You had mentioned there's on-road testing, especially if we go in the traditional kind of 26262 mind frame. But you brought up simulation, so there's different methods for validation. I don't know, Jocko or Ivan, do you have any, is there any kind of common validation methods that you guys use when you're developing your models?
I can start maybe even so we can jump in. Yeah, for sure. I mean, as Gokul said, it's over the years it became obvious that one must use layered approach, or as some call it, multi-pillar approach, where a combination of simulation, control testing on a proving ground, and test tracks, and together with real-world testing, and not to forget statistical analysis at the end, as well as formal safety engineering is used, since no single method is sufficient basically nowadays. And safety evidence must come from complementary validation pillars, where each one has some specific strengths and drawbacks. Gokul mentioned many of them basically already. And if you talk about ADAS and AD systems specifically, nowadays scenario-based testing is the standard, and the different methods ensure better test coverage in different areas. But thinking about AI models, I mean, see, nowadays they are taking more and more kind of the task itself. Like if you think about end-to-end models, they are doing pretty much everything, right, from the perception to the driving task. And that complex nature of learning mechanism behind AI models and the lack of deeper understanding behind AI models reasoning, we must admit that's the case. So we learn more and more about it, but we are not there yet, I would say. In order to make sure models are robust, without bias, accurate, etc., one must use layered simulations like model in the loop, software in the loop, hardware in the loop. Everything is needed basically to explore the design space as much as possible. Of course, simulations alone are not enough, and still real-world testing is a must, which includes orchestrated testing on a test track, as well as testing in the real world with real traffic conditions. And then we need to understand how simulations in many tools available nowadays to buy from different suppliers, which are trying to simulate both camera sensors output, radars, lidars, and so on. How they actually, what's the level of realism in those. How much can we trust those simulations and so on. But I would like to go back to one point which Gokul said, and I liked it a lot. It's about some scenarios which are either dangerous or really hard to actually test in a real world setup. Then you need to actually go to simulations and trust in simulations in those cases. And even NCAP tests today have some scenarios which are really hard to test on a proving ground, and regulators are willing to accept simulation results.
Yeah. And I think that's one of kind of the open questions between, simulation and, on-road testing or physical testing. Um, and I think the main point what you're saying is that there's not just one test that we can just
No.
claim, check the box and say we're
No.
done. It's going to be taken from a lot of different angles and a lot of different methods. Ivan, I know you worked with various customers, maybe some newer into ML development, things like this. Is there any kind of like shift of how organizations should think about validation in AI-based systems from kind of, especially for companies that maybe come from a traditional software background? Like, what kind of shift do you see these organizations need to make on validation?
Yeah, I believe the first shift in the understanding that is what Google already perfectly summarized. So already the ISO 8800 standard itself redefines the point of validation. So now it's not just are we testing the right thing, but actually the entire exploration of the operational design domain. So we are not just testing the behavior that we designed per our requirements, but also then exploring some emergent behavior that could have resulted from, let's say, our implemented safety mechanisms. If we retrained the network to alleviate for one issue, that it might spontaneously cause another one which we are not aware of, and this exploration leads us into the direction of reducing this unknown unsafe risks. Basically, we want to yeah reduce unpleasant surprises, so to say. And since the as we said, the entire operational design domain here is inherently not explicitly defined. So in the traditional software development, we had quite strictly defined operational design domain, and the entire design of the software would happen in the previous step when we are doing the requirements decomposition and architecture and system design. So in the end, the tests and verification themselves would be just, did we implement the right thing? But now, so we, yes, as I said, are testing, did we implement the right thing? But then also what let's say cover all of the possible edge cases. And then then we come also to the point of um, using the sequences and big data sets with the intent to have a statistical proof that our system behaves consistently and within our design in as much different scenarios as possible.
Yeah, and I think that's a key point, kind of in our traditional functional safety testing, we do requirements-based testing and you have a finite number of requirements. So you have kind of a finite number of test cases to run against. Also in our traditional sense, especially 26.26.2 or even 62158 really pushes a modular approach, like step by step, right? We do unit level testing first, and then we kind of put units together and we might do some kind of embedded software testing, and we're doing all that before we get into hardware software integration testing, all these kind of steps. And Draco, you mentioned end-to-end, and for those of you listening here that maybe not as familiar with end-to-end, because I know that term's used in many different cases. We talk about, communication can end-to-end protocols and things like that. But end-to-end in this sense is really going from pixel to control, right? And you have some
Exactly.
big LLM in the middle that just is able to take these pixels and, provide the control. Where, the term Gokul used in one of our previous fireside chats, the traditional AI, you'd break this up into chunks, right? You have reception area,
Yeah.
trajectory, and things like this. I guess this opens up to something that we see quite often talked about is like open loop evaluation, open loop testing versus closed loop. The open loop is more, let's evaluate at a model level, and then kind of closed loop is, well, how does it behave in its actual environment, the entire system? So I don't know, Jocko or Ivan, if you're able to talk about the differences between open loop and closed loop and kind of the importance of them, and maybe why, is closed loop very essential, for real world behavior?
Yeah, sure. I can start with it. So maybe just to take a brief look at the sort of basics about difference in between open loop and closed loop. I mean, since open loop and closed loop evaluation are focused on different aspects of AI model testing. In an open loop evaluation, the AI model is tested against a recorded data set. In open loop evaluation, it's used basically early and frequently in the development to train and compare perception, prediction, planning models or modules on a large data set. It's fast, provides us ability to iterate really fast. And we actually can extract objective model level metrics, which is really useful during the development phase. Some examples of frequent metrics are, for example, precision and recall for object detection. If you think about vehicles, pedestrians, traffic signs, etc. Maybe lane boundaries as well, if you have in mind the lane keep assist function or something like that. Although such information is extremely useful during development, alone it can be actually misleading, since at first glance, small error can in subsequent time point propagate further, basically accumulate over time, and lead in real world testing towards, for example, lane departure, if you think about lane centering or lane keep assist function. So if you accumulate every frame error in lane position estimation, then basically in real world testing, the car will depart from the ego lane, and you will not see that behavior, or it's much harder to anticipate such behavior in open loop testing. On the other hand, the closed loop evaluation incorporates the AI model in the complete driving system. So unlike in the open loop testing, here feedback loop captures how errors accumulate or diminish or interact with other components as well. And it's much easier to see if, for example, constant bias in the estimate of lane position initiate lane departure when it should not. Since every action system end up in a new state, and then sensors need to read that new scene. Sensors have a new and potential different view to the scene, not the same or very similar as it is in the case in the open loop testing, because you don't see in the open loop testing the results of the action you took in the previous time point. Maybe another interesting example is autonomous emergency braking, where in closed loop testing, after vehicle initiate hard brake, you can imagine a camera pitch angle. If you think about cameras, then pitch angle can change significantly and abruptly because the vehicle is braking. And that can potentially affect detection and tracking performance of the most critical object you have in front of the car, because which initiated brake at the beginning. And because of that sudden change in the calibration parameters of the camera, what can happen in theory, right, is that you get biased detections in those critical moments, which can either abort the braking when it's actually needed, or prolong it when it's not needed at all in case of a false brake, for example. And all that is really hard to see in open loop testing, and closed loop testing is kind of gold standard here for that. Also, I would say that open loop simulations have difficulties and require additional work to simulate and assess the robustness of the system under test against input signal changes. If you think about A/B function, so different sensor installation parameters, vehicle signals like velocity. I mean, you get the velocity from the vehicle bus, but that's not perfect signal. It has noise as well. Steering wheel angle, very important as well, but also noisy signal. And sometimes it's not even a symmetric noise, so you need to know basically how to model it. Um, Basically, everything can impact how the system behaves and how the system will be tuned at the end. So if you need to have a closed loop simulation to be able to tune different calibration parameters for the final vehicle function, which customer will perceive at the end, basically. So yeah, both have really pros and cons and need to be used for different ways and for different
I
purposes.
really liked your the AEB example, right? Because I mean, you highlight some key aspects of open loop testing where you can get some metrics maybe you can't see from the overall system. You can really hone in on a specific aspect of a model or a specific model itself. But I think the emergency brake scenario kind of introduces kind of the downfall, something you might not be able to see in an open loop evaluation of that model, just because of the dynamics of what's actually occurring at the vehicle level due to that.
Mm.
This reminded me, earlier this year, I was at the NVIDIA GTC in March in San Jose area, and there's a couple different thought processes or topologies that were discussed by the autonomous vehicle companies there. I mentioned about end to end, which is really this pixel to control.
Yeah.
But most of the vendors there, or most of the autonomous drive companies there, were more of a hybrid model. And I think that hybrid model allowed for kind of an open loop testing, but also you can obviously do the closed loop for a pure end-to-end. So there was a couple that are doing only pure end-to-end, no hybrid model, so no access really to perception in all these different areas.
Mm.
I guess in that kind of idea, there is no real open loop kind of testing possible, is there? I mean, if it's really purely end to end, like nothing, nothing I can grab in between, it's just feeding in a pixel and LLMs pushing out a control trajectory. Um,
Yeah, I mean, in that case, basically, you need to leverage simulations as much as possible, right? To use simulation tools which are available nowadays by different suppliers, where you basically have virtual worlds where you test most of the things. However, my personal opinion is that still real world testing is a must, and it's not possible to avoid it even in those cases. Um, Even though those models are progressing like really fast, and we have these chain of thoughts models and so on, which are trying to kind of explain to us in a natural language what they are doing and how they are doing, why they are doing it, and so on. But we always need to think about it, that part of the model which explain in a natural language to us as a user why the vehicle is doing what it's doing is also just an estimator.
mhm.
It can be wrong, right? And it can say something which will sound okay to us as a user, but actually it will not be fully aligned with the actual action decided in the other part of the model. So it's nothing is 100% in those models. So it's
So kind of the hallucinations that we saw early on with ChatGPT kind of exploded out there. You're saying you also can have in these kind of natural language translators.
yeah. So
So I guess
there
that
are,
really takes somebody knowledgeable to kind of understand if it's right or wrong, right? To some degree.
yeah, for sure. I mean, it's I would say it's no matter how big the model is, the problem is the same to really understand how the model
Mhm.
think, so to say. Uh, of course, it's more complex when the model is bigger and you need more, you have more tasks in it and so on. But still, the basic problem is the same or more or less everywhere. And once we solve it sort of in one domain, it will be much easier to solve it in the other domain. There are, of course, there is a progress available for sure in that area, but not solved completely yet. If you think about older, so to say, ways to solve if you have this modular approach you talked about recently, it's if you only think about perception modules, there is a progress, and we have a ways to understand, okay, why a model decided to not or detect something, or to do detect something as certain object and so on. But still, it's so many parameters in it. It's easy to end up with good statistics at the end, but to actually overtrain model perhaps in some specific scenario or and so on, which uh, just puts more and more attention to the data, basically, because data is kind of encapsulating requirements you mentioned earlier. You define how the system will behave by the data, actually, nowadays, more and more, and not anymore by writing requirements so much, but by writing data requirements instead. Yeah,
Yeah.
and yeah.
I mean, my
Yeah.
hopes in the long term is, at least for this modular approach, that the explainable AI methods will advance at least a little bit, so that at least those models will be deployable as the traditional software was. But now, as Drago said, we are still far away from that.
I mean,
I,
when you think about this question, you asked before, like comparison between traditional software development and now the situation with AI. At least I'm trying to explain to myself this as like looking at the standard V model and having the like developed software in the cross section below, right at the bottom of the V. And now that part is becoming AI model, which is just growing and eating more and more of the V model. And it's some connections are, so let's say, broken and need to be rebuilt in a different way, and that's why we see now the way attempts to patch sort of by introducing additional V models just for data, just for this, just for that, and so on. So, yeah.
well, Ivan, you kind of made an interesting statement, and I kind of struggle with the whole explainable AI
Mhm.
aspect. So, if we look at EU AI Act, and if we look at ISO IEC 42001, there's discussion about transparency, and about your processes and things like this, but there's also, oh, we should have explainable AI models. And I think in maybe simple financial models, right? Like if we have a financial AI model that determines who gets selected for a mortgage or who gets selected for a loan, I think you can kind of have a parallel model run and kind of get explainability. I struggle a little bit in the direction that maybe a lot of companies are going to with these huge LLMs. They're kind of doing generalization, right?
Mhm.
Like, does it really, there's a huge effort to get explainability. And as these models get larger and larger, I mean, is it worth the effort, or is it even possible to get really true explainability?
Yeah, and if we are depending on another model, then we come into the same trap that Drago already mentioned. If whether this or how the second model interprets the first model, whether this is trustworthy again. So it's basically then gets recursive.
Mhm. Yeah.
It is interesting, right? Like there are certain physical AI applications where it's slow enough that you can do that, but particularly autonomous drive is going to be hard, right? You could argue maybe autonomous trucking, you could potentially run those models in the cloud and maybe you have enough time. But Jody, I agree with you. Like particularly for driving, it's hard to get that explainability real time. But for the robotics, I think you can. So maybe it's an interesting sort of topic for
Mm.
physical AI overall, but maybe with autonomous cars, it's going to be just harder to get that explainability.
Yeah. Well, cool. I guess kind of on this, I mean, we've highlighted some of these points, but I think the one thing that a lot of our customers talk about and everybody's trying to get their hands around is, why is it so difficult to define what sufficient validation is, and I mean,
Yeah.
can we draw a line in the sand in 2026? I mean, obviously we're going to know more in 4 or 5 years from now, but is it possible to draw a line in the sand today and say this is sufficient enough for now, or?
No, and I think the UNECE group, the WP29, came together, worked on it for many years, and still what they came out with was qualitative, right? Competence-based or evidence-based sort of argument. So I think it's because of the inherent probabilistic nature and also the unlimited scenarios that are out there, right? So in a way, I think we can't get to a very satisfying answer there because of maybe in some cases when we have these physical AI systems with a lot of use cases, even tight use cases, very very specific use cases, then I think maybe it's possible that we can go through all of these scenarios and maybe gain some. So if the ODD is very restricted, then it's possible. But then you start running into the trade-off that maybe the product is not as useful, right? You were talking about generalizing and having more capability. So in a way, what is good has always been in comparison with some benchmark, right? In autonomous drive, it's in comparison with a good human driver benchmark. Of course, we can all argue like what is a good driver, right? Like, we know AV companies say, oh, there are people who are driving the car distracted and driving the car inebriated, right? Therefore, our cars are not going to do that. Our cars won't get fatigued. They won't drive when they're sleepy. So there's an argument that they push that there is and I've seen this where they say not implementing or not having autonomous vehicles out there is irresponsible, right? Sort of there is that argument, but I think our view, or at least maybe I should say my view, and also what the UNECE their view is, the benchmark should be a careful, non-distracted, competent driver, right, in an autonomous driving context, and you need to be at least as good as a careful defensive driver, right? So that is a good benchmark. Of course, that still doesn't answer what is good enough in terms of validation, but at least you can start comparing. Maybe we do have accident databases and accident studies. Of course, we know fatalities and injuries are better documented, and therefore we have good data. Of course, we don't get data on fender benders and where injury did not occur. So in those cases, we are not always able to compare apples to apples. So therefore, good enough is basically how good the benchmark information is. So we need to think about two things, right? One is how can we build a good acceptance criteria? And I'm using a sort of term here of building a good comparative metric that we can say this is as good as a careful, competent driver. And let's say a behavioral competency of a ADS is similar to a competent driver, and that's what we are trying to do. And then we go through the scenario exploration space to make sure that hypothesis still holds true. But then it's not enough to just say I've simulated 10,000 scenarios or 100,000 scenarios, right? You need to still build a credibility argument. And that credibility argument is basically, have I representatively tested across my ODD, right? If I'm using a benchmark to a human in my ODD, and let's say my ODD includes light rain or heavy rain or snow, have I tested across those? Have I stress tested my ADS model the same way people were stress tested in their real world driving, right? So that's the credibility argument becomes really important. And that's how you argue that your data or your metric is correct. Also, I think it's really hard because we cannot always know what the unknowns are. Therefore, what we can reasonably do is defend with the information we have, second set of eyes check, and confirm that this is we did a good faith approach to come up with a number, and we are going to test against it. Of course, that's where you have a concept of a safety case and convincing external people so that if, let's say, your safety case is invalid in the field, you still have an operational concept, some governance to re-review, maybe have some way of confirming if you have an out of distribution type of event, or was it just a gap? Maybe you need to ground the fleet, or maybe you need to take away your robots from particular factory because that environment was not covered in your test cases, right? those are the cases that I think, I don't think, unlike the rules-based or traditional systems that we're talking about, here I think the safety problem is very much a development problem, but also an operational problem, right? Making sure that we are still having a valid, complete safety case. We should expect corner cases in the real world, right? It shouldn't be ignored. We should expect corner cases to happen almost on a daily basis, and our processes should cover for that.
Yeah, and I mean you're bringing in a lot of these kind of SOTA principles also in this discussion, the ISO 21448, and one of the I guess key talking points in that standard is this idea of functional insufficiencies, and then how triggering conditions and kind of like tweak those out or bring those out where they could potentially cause an issue. That idea, I mean, when the 21448 came out, is really kind of more vehicle system level discussion, but it is also very applicable at the data set level. I know Visage recently released a white paper about kind of data set insufficiencies. I don't know, Jocko, Ivan, if you're able to maybe kind of walk us through that white paper and kind of maybe some of the key points there.
Yeah, sure. So yeah, it's essentially our white paper is focused on the insufficient system performance as a result of dataset insufficiencies. Mentioned a couple of times already. Data is becoming the crucial part of everything, and since data plays that major role in AI training and testing, similar insufficiency in test and the validation data can produce basically a systematic fault, which will pass under the radar. You'll not see it. And those insufficiencies can go from all the way specification level to the performance level. Like more specifically, if you talk about vehicle level function specification, basically it's not translated in a good way to the data specification. And that can give, as a result, an AI model which has insufficient performance or even completely lacking performance with respect, I don't know, for example, some specific type of object class or similar. You just miss that type of object because you didn't define data set requirements and everything going with it in a good way. And the paper describes this in a nice way, using concrete examples from public data set, how data set lifecycle looks like, and what are particular properties which data should satisfy from safety perspective, of course, ensuring that safety-related properties like relevance, completeness, balance, correctness of labels or annotations, traceability, etc., are present right from the start of the product development. And that can save a lot of pain and working hours later in the development. One interesting example is the choice of hardware. Like when you think about data collection as an extremely important and super expensive step in the development, one can imagine that organizations can have tendency to cut the cost somewhere, right? And this could be one of the tempting places to do savings while choosing the hardware. So it's obvious, since if you don't want to collect more data, so if you want to collect more data with different hardware, you need to buy more equipment, right? And build more cars, probably drive around more overall, and ensure support for various types of hardware, etc. However, going further, that diversity in dataset later in the development will likely pay off by providing more robust AI models, and investment will likely pay off by having less reported insufficiencies and more safe system on the road. And this paper also gives some practical advices about metadata tags and how to make use of it, as well as labels and labeling process, and how important it is for the entire AI model and therefore entire system development. I don't know, Ivan, do you think I missed something? I try to kind of summarize it
Yeah,
briefly.
I think you covered it quite well. So the sources where we get at all of the information there was, for one, the ISO standards, but we also referenced the AMLAS and CODAN
Yeah, true.
papers, yeah, which might be of interest to the listeners. So I don't know if you are familiar with it or not. So basically, those are um, papers or other publications that were issued before the ISO 8800 became official. They were attempts to standardize, rather to introduce a process of how to formalize the life cycle for um, um, machine learning in autonomous systems. So the AMLAS was published by the University of New York, and I believe CODAN was by the European Aviation Agency or something. And so the gist in them is they both focus on the safety argumentation through the life cycle. So again, as Gokul mentioned before, since the ISO 8800 itself also doesn't say where is enough validation, the same way in these standards, they are also not putting a definitive limit. This sufficient validation, but instead introduce several steps within the life cycle of the model through which, if we provide the argumentation, we prove that we did our due diligence to make the model safe and to consider potential unknown risks. And in our work, in our white paper, a lot of conclusions basically converged into similar conclusions from all of the three works. So, for example, we have references on dataset properties, which in the end quite correspond to each other or are, let's say, mappable. Then the requirements definition and the process how the data requirements need to be defined again converges on similar conclusions. But it's still interesting to see how this was done. As I said before, the ISO standard was officially introduced.
Yeah, I mean, this sounds really great. One of the things, obviously, the ISO Pass 8800 is relatively new, and I think there's a next edition that's being worked on that will be released shortly at some point here. But the fact that your paper brings in some practical aspects, I think, is very helpful for the community because we have access to the 8800, and I think it has really a lot of good ideas in it. But sometimes it's hard to visualize and hard to envision for the practitioners actually how to apply it without having these actual examples. So I think it's great that you're able to take in some like publicly available information and kind of expand it out and show it works. One of the
And if I
interesting,
may,
yep, yep, go ahead.
if I may just add, so additional benefit of those papers is their size. So they're significantly shorter than the ISO standard, but still
Yeah.
brings some valid points. So, for example, in my case, the life cycle described in AMLAS is much more, let's say, easier to overview and understand for a novice going into this area.
hmm No, that's great. And one of the things that you mentioned, and also the 8800 brings out, we always have life cycles. We talk about the safety life cycles and things like this. But the one thing I really like the 8800 kind of drove in well is the data set life cycle, right? Like where it introduces that. And I think for those working in ML, I mean, you're really driven by this data. I did just want to transition the discussion a little bit. I know we're kind of running up on the time. There's a new idea that we're seeing. For example, it's in the ISO ICTS 22440. So 22440 is kind of our agnostic to industry AI functional safety standard, and it hasn't been released yet, but there's kind of drafts for the working groups. But it brings in an idea that the 8800 is going to be bringing in as well as this kind of uncertainty quantification, this UQ idea. And I think it's an interesting thing that we should talk about here because a lot of times when we talk about ML development, we always talk about the certainty of something. So I'm 95% certain that's a dog, or I'm 95% certain that's a pedestrian or whatever. But this kind of flips that discussion a little bit on, well, how uncertain am I, or how unsure am I about the AI system? We see the 22440 bringing this in, and there's actually a new standard in the works that's also not released yet. So I mean, we're working kind of in this gray area right now. But the ISO IEC 25223, it's currently under development. I don't know, go cool. Maybe just quickly, if you can kind of walk us through some of the main principles there, because I think like moving forward, once all these are released, there's, is going to be an interesting topic to come back with this validation discussion.
Yeah, we're all eagerly waiting for this 25223 standard, because I think it's not only helpful just for like an agnostic AI system, but also I think we can build a tailored version of what that is for even autonomous vehicles, right? There is some that's already being done. So this upcoming standard 25223 is basically trying to build a shared vocabulary, right? When we talk about uncertainty, all of us, the four of us here, will have our own idea of what uncertainty is, right? And of course, 8800 gets into it a little bit, like model observation uncertainties, these sort of things. I think the standard does a good job of trying to come together and sort of define what uncertainty is and what sort of uncertainty are we really looking for. And then they do talk about three types of sources of uncertainty, three runtime sources. They take this ML uncertainty into a model fit uncertainty, right? The sort of what we call is like, did we pick the right model? And there are some uncertainties around that. Or those uncertainties could lead to output insufficiencies of the ML model. Also, there is this input quality uncertainty, right, of the input space. For instance, let's say there's a stop sign and then there's snow that's obscuring the stop sign, right? There are some uncertainties out there, noise that could be out there, potentially even like adversarial attacks that look like sort of uncertainties, right? So that's another thing that's the model, the standard talks about. Also, there is this scope compliance uncertainty, right? Let's say we take an ADS system that's modeled using European or German traffic signs, and then now you're taking, let's say, this zero-shot sort of approach. You're putting it in the US and seeing how it works. Then you're going to have uncertainties, right? So these are the way that the standard sort of defines it, and it's easy to sort of think about. Also, they talk about the inherent, the aleatoric, and of course the knowledge-based or knowledge gap-based epistemic uncertainties that we've sort of had some discussions on in the past. So really, the standard does a good job, at least so far in draft form, to catalog these uncertainties so that everybody can understand. Also, maybe that can be used to build some metrics, and in 22440 they do provide some metrics on how to build during your model development process, maybe building some metrics for uncertainty quantification, but also having uncertainty quantification during runtime, right? Confidence metrics and Brier scores and those sort of things that you can build as well. So it's a good, I think it brings everybody to the same page in terms of talking about this uncertainty and how to build metrics around that. Knowing us, right? Like we work not only in autonomy, but also in physical AI and robotics. The standard is still valid in both domains. We just have to ask the contextual question of what uncertainty means and what should we track in each of these domains.
Yeah. And I think this gives us another tool. I mean, Jocko kind of walked us through validation methods. It gives us another tool that can be used in both simulation and kind of closed loop testing as well, and environmental testing as well. I guess to that point, I'd be interested in anybody here, like will we ever reach a point like from a pure simulation? So now we have these uncertainty quantifications we can do and all these different techniques. Will we ever reach a point where simulation can replace the majority of real world testing? Because going back, Gokul, you kind of mentioned about some of the challenges and, comparing real world data. Well, I think in the US, we're around 3.2 trillion miles every year driven. It's hard to get those road miles on vehicles. You can even see the leaders out there. Nobody has 3.2 trillion miles, driven autonomously. So, like, what are any thoughts on like simulation? Can it ever replace real world or?
Yeah, I personally, well, I would very much like for it to happen because, as you said, it would simplify a lot of things. But in the end, the simulated data still does have a lot of weaknesses. So yeah, in order for it to at least be somewhat viable, we first have to qualify it against real world data. So you already have a need for real world data for the qualification, either for the simulation tool, uh, and then this requires much more data, or to validate the created simulation data before it. So from an tool that might be not qualified itself, but you can still qualify the data that comes out of it by comparing it again to the real world data. So yeah, I think we will not get rid of real world data anytime soon, but yeah, with the quality of simulations, they might play a bigger and bigger role, basically a bigger chunk of it in the entire data sets. But yeah, maybe it's just I don't know. What are your experiences there on this?
Maybe I'm old-fashioned, I guess. I think there is this real like sim to real gap, even in closed loop simulation, right? That's a big concern. Of course, it's the gap is closing, but particularly with throwing more compute at it, the gap seems to close more. And computers getting cheaper, not because of just automotive, but other LLM sort of transformation that's out there. I think um, credible organizations that are in autonomous robotics, autonomous driving, they recognize, and we all recognize, right? It's impossible to scale a real world fleet to get that same level. However, real world fleets are what you can use for breadth testing, right? Which is trying to get a few of these out there and trying to operate across your ODD, right? And even the leading ADS players are only doing what, few million miles a week, right? So Judy, to your point, they're never going to achieve that level of scale, right? But they're going to see edge cases. We do see, right, on social media, on LinkedIn, wherever, edge cases happen all the time. And when edge cases happen, then it's a great input for your simulation tool to go and do a lot of depth testing, right? So it's still useful to explore because the simulation environment, the physics engine that's there, is still fed by the real world. Of course, the world keeps changing. There is drift in the world also. So it's still helpful. I think completely replacing it would be again, maybe I need to take my words back in a few years. I think that's impossible. But I think with more compute and better closed loop simulation, I don't think we need as much, even the scale of real world fleets that we need today, right? To do the same thing. Interested in any counterpoints to that also. That's my sort of current view.
No, I would more or less agree, but also one thing that makes, in my opinion, a difference is which part of the AI lifecycle the synthetic data is used. So in the test and validation, it makes much more sense since it's already been trained. If it's already been trained on a combination of synthetic and real world data, but in the training itself, I do not think we can replace it simply because of the nature of the ML models. So they tend to take shortcuts in learning. So, for example, if you have a simulation that has some, let's say, two perfect annotations or two surfaces that are too smooth. So, in these cases, the LLMs not LLMs, the neural networks tend to take shortcuts and then maybe learn by surface instead of learning by shape, which would happen in a naturally annotated data. Or maybe the annotations themselves get too perfect, so they learn on particular rendering type or shadow, let's say, something like that. So yeah, this then makes a huge difference. And in testing, as I said, if you have already trained on features that came from a real sensor with some deviations in annotation, then you might, let's say, use the simulation to generate those cases that are either prohibitively expensive or dangerous to actually record in real world.
Seems, Jody, like you hit the right point with this with this question. Can I give my 5 cents to this topic as well? Do we have enough time? I mean, the improvements done the last 5 years are massive, right? And high fidelity we see today is even hard to compare what we had just a few years ago. However, I would say that the main challenge still remains open, like how to make models more realistic in a sense that to be less perfect. and how to prove, and when to decide that some parts will be tested only in simulation. Like in my opinion, here we also see another flavor of the same issue, like the level of understanding how AI models reason or think. Like once we understand that better, then we will might have a chance to build even better synthetic test data, because weak spots then will be more clear to us. I mean, what's interesting, even if you look like, as we mentioned, latest NCAP tests, some scenarios like head-on oncoming vehicle scenarios, if you're familiar with the NCAP test scenarios, are really tricky to execute on a test track. And regulators are willing now to accept simulations as part of the proof. So I would say the future is more and more in simulations. There is no doubt in that. But the question is where we will completely switch, and if we will ever completely switch. Yeah. I hope not, honestly, but let's see.
Yeah, I don't think any of us safety people would be very comfortable in purely
Yeah.
simulation, but yeah, I mean the augmentations and things we can do in simulation, and kind of go cool's point in a couple of years from now, we don't know what we don't know, but I mean it is evolving, and physical simulations are getting better, everything's getting a little bit better. Well, I think we could talk probably for another hour easily, but we need to kind of close up here. Any final comments before we end here, or?
I think the data lifecycle we did talk about. I think whenever we've trained the 8800 or the ML lifecycle, we've seen that engineers are doing that, but maybe not as formally, right? To really try to limit these uncertainties, because engineers tend to think about faults. Those are easy to see. They think about these edge cases. Those are, once you see them, you can see why they're problematic. But these uncertainties are hard, right? So having this view of thinking about the data and what sort of data quality things you need, where the uncertainties can come from, I think it's a new domain. I think it's helpful for us here to talk about it, but also it's helpful to talk about it with your ML and data teams, right? They may be thinking about it, maybe they don't have a framework to talk about it. I think this will give a good framework for that.
Yeah. Great. Well, thank you, Goko. That's a great ending statement. And thank you, Draco and Ivan, for joining us. This is very interesting. We learned a lot here. For
Thank
everybody
you.
listening in, thank you for joining. Feel free to reach out to us with any further questions. Thank you all.
Thank you.
Thank you.
Bye.
Bye bye.